Welcome to another deep dive. Today we're going to be going into the world of mathematical physics.
Okay.
We're going to be looking at some really cool concepts from a 1993 conference
Oh.
on differential geometrical methods in theoretical physics.
Yeah.
This conference was actually a tribute to the physicist Conrad Bleuler.
Okay.
And the excerpts we have are kind of like a time capsule of cutting-edge ideas
Right.
from that era.
Yeah.
So get ready to unravel the mysteries of
Whoa.
quantum groups, braided geometry, and their surprising applications in theoretical physics.
It's amazing how these concepts,
Right.
which might seem very abstract at first,
Yeah.
offer profound insights into the nature of reality itself.
I think that's what's so cool about this, is that it's
Yeah.
this intersection of math and physics and,
For sure.
these things that seem so theoretical
Yeah.
actually have very practical applications.
Yeah.
And this conference was really a testament to Bleuler's vision of fostering this collaboration between mathematicians and physicists.
Right?
He was really big on encouraging young physicists to tackle fundamental questions.
Yeah.
And the spirit of collaboration is really evident in the excerpts we're going to be looking at today.
Right.
One of the most intriguing connections, I think,
Okay.
that we see in these excerpts is the connection between quantum groups and knot theory. So can you kind of help me out here?
Sure.
What exactly are quantum groups, and
Right.
how do they relate to something as visually intuitive as knots?
Well, you can think of quantum groups as a special type of algebraic structure
Okay.
called a Hopf algebra.
Hmm.
And they provide a really powerful mathematical language to describe and analyze knots.
Okay.
So in knot theory, you're essentially studying the different ways you can tangle and untangle loops, and quantum groups provide a way to classify these knots and create something called invariance of three manifolds.
Okay.
So imagine a three-manifold as a higher dimensional space, and these invariants act like unique fingerprints, helping us understand its shape and properties.
So we're going from knots
Yeah.
to the structure of space-time.
Right.
That's quite a leap.
Yeah, it's pretty amazing.
The source material mentions a specific quantum group
Okay.
called UQSL2.
Yeah.
Which plays a key role in generating these three manifold invariants.
Right.
So what makes this particular quantum group so special in this context?
UQSL2 is really fascinating because it has
Okay.
a very rich mathematical structure that lends itself very well to the study of knots and three manifolds.
Okay.
It allows you to create these invariants that capture
Okay.
essential topological information.
Right.
You can think of it as a mathematical tool that lets you untangle
Yeah.
the complexities of higher dimensional spaces.
That's incredible.
Yeah.
The source even hints that these mathematical tools
Right.
might be useful in understanding quantum gravity.
Yeah.
Which is, that elusive theory that's trying to unify quantum mechanics and general relativity.
Yeah, for sure.
Seems like we're peering into the very fabric of the universe here.
It's pretty mind-blowing.
Okay, let's move on to another really cool concept, braided geometry. So the source describes it as a world where the familiar rules of geometry are twisted.
Right.
Sounds a bit like something out of Alice in Wonderland.
Yeah, it is a bit trippy.
So how does this twisting work?
Okay.
And what are the implications?
In braided geometry, we encounter this concept of quantum spaces
Okay.
where coordinates might not commute. In classical geometry, the order in which you multiply coordinates doesn't matter.
Right.
You can think of it like moving along a grid.
Okay.
Going north then east gets you to the same point as going east then north.
Yeah.
But in braided geometry, this rule breaks down. The order of operations suddenly matters,
Okay.
leading to some very counterintuitive results.
So it's like saying in this twisted world, your path depends on the order in which you take your steps.
Exactly.
You could end up in a completely different place just by changing the sequence of your movement.
Yeah, it's like a whole new set of rules.
The source mentions something called the algebra of braided matrices,
Okay.
which acts as a quantum analog to functions on a manifold. So can you unpack that for us?
Sure.
What does it mean for something to be a quantum analog in this context?
So think of a manifold as a smooth, continuous surface,
Okay.
like a sphere or a donut. In classical geometry, you can describe functions on these manifolds
Right.
using regular numbers and variables.
Yeah.
But in the quantum world, things get a little more complex.
Yeah.
The algebra of braided matrices allows us to define functions on these quantum spaces.
Okay.
Where the coordinates no longer behave in a classical way. It's kind of a way of translating the familiar language of geometry into a language that can handle the strangeness of quantum mechanics.
So it's like we're building a new kind of map to navigate this uncharted territory where the rules of space and geometry are fundamentally different.
It's a whole new world out there.
But how does this all connect back to the real world?
Okay.
The source mentions something called Q-deformed physics.
Right.
So can you shed some light on that for us?
Sure.
What does it mean to Q-deform a physical theory?
Q-deformation is essentially a way of introducing a parameter called Q that controls the level of quantumness in a theory.
Okay.
In classical physics, everything behaves nicely and predictably.
Right.
But in the quantum world, things get fuzzy and uncertain.
Yeah.
Q-deformation allows us to dial up or down the quantumness of a theory, giving us a more nuanced way to describe physical phenomena.
So that's really interesting. So it's like a knob.
Yeah, exactly.
That we can turn to adjust the level of quantumness.
It's a pretty neat concept.
A great example that the source gives is Q-Minkowski space. No, Minkowski space is the framework for Einstein's special relativity, right?
Exactly, yeah.
Where space and time are intertwined.
It's a four-dimensional space that describes the geometry of space-time.
So in Q-Minkowski space, we introduce this Q parameter, which makes the coordinates of space-time non-commutative.
Exactly.
This means that the order in which you measure space and time suddenly matters.
Right.
Challenging our fundamental understanding of how these concepts are related.
It's really mind-bending.
Yeah, so instead of a smooth, continuous space-time, we have a space-time where things get a little jumpy and unpredictable.
It's like the fabric of space-time is getting a bit fuzzy.
Depending on the order of measurement.
Exactly.
Okay, that definitely challenges our intuition.
It does.
The source also mentions a connection between Q-Minkowski space and spinors, which describe the intrinsic angular momentum of particles.
Yeah.
So what could this connection tell us about the nature of space-time itself?
It's a really tantalizing clue that suggests a deeper relationship between the structure of space-time and the properties of elementary particles. Spinors are these curious mathematical objects that describe how particles rotate.
Yeah.
And their connection to Q-Minkowski space hints at a deeper level of structure that we're only just beginning to understand.
It's as if the quantumness of space-time is somehow encoded in the very way particles spin.
It's a fascinating idea.
That's incredible.
Yeah.
It seems like every step we take in this deep dive reveals another layer of complexity and interconnectedness.
Yeah, for sure.
And we're just getting started.
I know, right?
There's so much more to explore.
Yeah, definitely. Welcome back to our deep dive into this fascinating world of mathematical physics.
Yeah, it's really exciting to see how these abstract concepts we were talking about can actually be applied to concrete physics problems.
Absolutely. So the source material highlights
a particularly interesting application, I think, in the realm of quantum gauge theories. Now, quantum gauge theories are really the foundation for understanding the fundamental forces of nature, right?
Exactly.
Like electromagnetism, the strong and weak nuclear forces.
Yeah, they're the forces that basically hold the universe together.
So we're talking about some pretty important stuff here.
Yeah, for sure.
And the source material dives into the challenges of computing something called commutator algebras of Wilson loops. In these theories. Okay, I have to admit, those are some pretty intimidating terms.
Yeah, they could be a bit of a mouthful.
Can you break it down for me?
Yeah, absolutely.
What are commutator algebras and Wilson loops? And why are they so important in this context?
So in quantum mechanics, you can't always measure two quantities simultaneously with perfect accuracy.
Yeah, that's the Heisenberg uncertainty principle.
Exactly. That's the famous one.
Yeah.
The commutator of two operators tells us how much these quantities can be measured together. A Wilson loop is a special kind of observable in quantum gauge theories. It's like a measuring stick that helps us probe the behavior of the gauge field along a closed loop.
So by calculating the commutator algebra of these Wilson loops, we're essentially trying to figure out how much we can know about the behavior of these fundamental forces in the quantum realm.
It's like we're trying to peek behind the curtain of quantum uncertainty.
And this calculation turns out to be quite challenging.
It is, yeah. It really highlights the complexities of quantum gauge theories.
So the tools that we were discussing earlier, like quantum groups and braided geometry, offer new ways to approach these problems.
Yeah, they give us a new perspective on these really tough calculations.
It's like we're developing a whole new set of mathematical tools.
Yeah, it's like a new toolbox.
To explore the quantum world.
For sure.
The source material also mentions using Q-deformed structures to understand quantum mechanics itself.
Yeah, it's kind of a recursive idea, isn't it?
Yeah, it's fascinating that we're using the concept of quantumness to understand quantum mechanics.
It's like using quantum to understand quantum.
Yeah, exactly. Can you elaborate a little bit on how Q deformation provides these new insights into quantum mechanics?
So Q deformation allows us to introduce this Q parameter that basically modifies the usual rules of quantum mechanics. For example, we can consider a Q-deformed harmonic oscillator. You're probably familiar with the classical harmonic oscillator.
Yeah, they're like a mass on a spring.
Exactly.
Where it oscillates back and forth with a certain frequency.
Right, so in quantum mechanics, this becomes the quantum harmonic oscillator with these quantized energy levels. Now, by introducing Q deformation, we actually change the spacing of those energy levels, leading to new and unexpected behavior.
So it's like we're tweaking the energy levels of these quantum systems, and that leads to a deep understanding of how they behave.
It's a really powerful tool.
That's really cool. The source even hints at a connection between Q-deformed geometry and string theory. Now, string theory posits that the fundamental building blocks of the universe are these tiny vibrating strings.
Right. It's one of the most mind-boggling concepts in physics.
It is.
I mean, tiny vibrating strings making up everything.
It's hard to wrap your head around.
It is.
So how does Q-deformed geometry fit into this picture?
Well, Q-deformed geometry introduces a different kind of geometry that could potentially describe the space in which these strings exist. A very speculative idea. But it shows the potential of these mathematical tools to really push the boundaries of our understanding of the universe.
It's like we're opening up a whole new dimension of possibilities. I love that.
The source also mentions a connection between something called topological field theories and string backgrounds. I have to admit, I am completely lost here.
Well, let me try to guide you through this. Topological field theories are a special type of quantum field theory that focus on the global properties of space-time, like its shape, rather than local details like curvature. String backgrounds refer to the specific configurations of space-time in which strings can exist.
So it's like the shape of space-time determines how the strings vibrate and interact.
That's the basic idea, The source material suggests that topological field theories can be used to study these string backgrounds, potentially revealing deep connections between the geometry of space-time and the behavior of strings.
So it's like using the shape of the universe to understand the fundamental nature of matter and energy.
It's a pretty amazing concept. That's mind-blowing. The source also delves into this world of non-abelian Chern-Simons vortices, which sounds incredibly complex.
Yeah, it's getting pretty deep into the theoretical weeds here. But Chern-Simons theory is a type of topological field theory that finds applications in condensed matter physics and particle physics. Non-abelian Chern-Simons vortices are these special types of topological defects that can arise in these theories. They carry topological information and can be classified using techniques from knot theory and group theory.
So we're connecting back to knot theory again.
It all comes full circle.
It's amazing how all these different areas of mathematics keep intersecting.
Yeah, it's like they're all different facets of the same underlying structure.
Can you give us maybe a more tangible picture of what these vortices are and why they're so interesting?
So imagine them as these tiny whirlpools of energy and charge that exhibit this unusual behavior due to their topological properties. Studying them could actually lead to insights into exotic states of matter and new phases of quantum field theory.
So it's like we're discovering a whole new zoo of particles with strange and wonderful properties.
It's a pretty exciting time to be a physicist.
This source material also introduces this concept of Q quantum mechanics.
Right.
Which sounds like we're adding another layer of quantumness.
Yeah, exactly.
On top of what was already a pretty quantum concept.
It's like quantum squared.
So what makes Q quantum mechanics so unique?
Well, Q quantum mechanics takes the idea of Q deformation even further, leading to even more radical departures from classical physics. One of the key features is a modification of the Heisenberg uncertainty principle.
Okay, so in Q quantum mechanics, things get even fuzzier and more uncertain.
Yeah, it's like the universe is becoming even more elusive and mysterious.
The mysteries just keep deepening. The source material also revisits the topic of C-star algebras.
Right.
Hinting at even deeper applications in quantum physics.
Yeah. C-star algebras are such a powerful tool for describing quantum systems. One particularly intriguing application that's mentioned in the source is their use in describing the quantization of space-time itself.
Okay, quantizing space-time.
Yeah.
That sounds like a monumental task.
It is.
What does it even mean to quantize space-time?
It's essentially about trying to reconcile quantum mechanics with general relativity, which describes gravity as this curvature of space-time. Quantizing space-time means finding a way to describe space-time in a way that's compatible with the principles of quantum mechanics.
So it's like we're trying to make gravity play nice.
Exactly.
With the quantum world.
Yeah, it's one of the biggest challenges in modern physics.
And C-star algebras offer a potential framework for doing that.
They do. Yeah, it's a very active area of research.
It seems like every path we explore leads us closer to this ultimate goal of unifying quantum mechanics and general relativity.
It's the holy grail of physics.
The source material also throws in something called free fermion constructions, which I'm not familiar with at all.
Okay, so free fermion constructions are techniques that are used in string theory and conformal field theory to build models with specific symmetries and properties. They involve using particles called fermions as building blocks to construct more complex theories.
So it's like using Lego bricks to build different structures.
Yeah, that's a good analogy.
But the bricks are these fundamental particles called fermions.
Exactly.
And the source material highlights how these constructions can be used to explore the relationship between different types of string theory. And to understand the emergence of symmetries like supersymmetry.
Supersymmetry is this really elegant concept.
Yeah, it's the idea that every particle has a partner particle with a different spin.
It could help solve some of the outstanding problems in particle physics.
It seems like every concept we've explored so far leads us to even more fascinating and complex ideas.
Yeah, that's the beauty of physics.
The source material also touches on the world of geometric algebra and its potential to revolutionize our understanding of physics.
Geometric algebra, also known as Clifford algebra, is this powerful mathematical framework that unifies vectors, scalars, and higher dimensional objects into a single algebraic structure.
Sounds like a mathematician's dream come true.
It kind of is.
But how does it connect to physics?
Well, geometric algebra provides a more elegant and intuitive way to describe physical concepts and theories. For example, it can be used to express Maxwell's equations of electromagnetism in a remarkably concise and insightful way.
It's like translating a complex symphony into a single, beautiful melody.
I like that analogy.
And the source material even suggests that geometric algebra could offer a path toward a more unified description of physics, where different forces and phenomena are seen as different facets of a single underlying geometric structure.
It's like saying the universe is at its core.
Yeah.
A symphony of geometry.
I love that.
It's a beautiful thought.
We've covered a lot of ground in this part of our deep dive.
We have.
From quantum gauge theories to string theory and the quantization of space-time. It's been an incredible journey.
It has.
Through these frontiers of mathematical physics.
I'm ready for more.
And we're not done yet.
Oh, good.
And the final part, we're going to explore even more mind-bending concepts. Including something called polydimensional covariance, which challenges our very notion of dimensions.
Okay, bring it on.
So get ready for another thrilling ride.
I'm strapped in.
Through this landscape of theoretical physics. Welcome back to the final part of our deep dive. It's been quite a journey exploring this intersection of mathematics and physics.
It really has. Yeah, it's amazing to see how these abstract mathematical tools can help us understand some of the biggest mysteries of the universe.
I'm ready for more.
Okay, good.
In this last part, I really want to dig into some of the more unconventional and thought-provoking ideas from this material.
Right.
And one that really caught my eye was this concept of polydimensional covariance.
Yeah.
It sounds like something straight out of science fiction.
It does. It's a very challenging concept. It really pushes our understanding of dimensions in geometry.
So how would you explain that to somebody who, doesn't have a background in theoretical physics?
Imagine a world where what you perceive as a line could be seen as a plane or even a higher dimensional object by someone else.
So it's like saying that dimensions themselves become fluid.
Exactly.
And relative to the observer.
Yeah, the very fabric of space could be perceived differently.
That's a pretty radical departure from our usual way of thinking about dimensions.
It is. Yeah, it's a very different perspective.
Does the source material give us any clues as to how this concept might be applied in physics?
It suggests that this framework of polydimensional covariance could potentially lead to a more unified description of physics, where different forces and phenomena are seen as manifestations of a single underlying structure.
So it's like a grand unified theory of everything.
That's the hope, yeah. It's a very ambitious goal.
And the source even proposes using a dyadic Clifford algebra.
Right.
Which is essentially a doubling of the usual Clifford algebra.
Exactly.
To represent this richer geometric structure.
It's like we need a more powerful mathematical language to even describe this polydimensional world.
What are the implications of using this dyadic Clifford algebra?
Well, the source explores how this dyadic Clifford algebra could actually be reinterpreted as a single 8-dimensional multi-geometric space.
Wow.
Potentially offering a framework for unifying different aspects of physics.
8 dimensions. That's even more mind-boggling than the extra dimensions.
Right.
Proposed by string theory.
Yeah, it's a very bold idea.
What's even more intriguing is the mention of a multi-vector Dirac theory.
Right.
Formulated in this 8-dimensional space.
Yeah. So the source suggests that this multi-vector Dirac theory could potentially represent all the fundamental fermions of the standard model of particle physics.
So fermions are the particles that make up matter.
Exactly. Things like electrons and quarks.
So we're talking about a single mathematical framework that could encompass all the known particles of matter.
That's the idea. It's a very ambitious goal.
It's a pretty bold claim.
It is, yeah. Much more research is needed to see if it can be fully realized.
It's like we're trying to piece together a giant cosmic puzzle.
I like that.
And polydimensional covariance might just be a crucial missing piece.
It could be, yeah. It's a very exciting possibility.
The source also mentions the possibility of matter-antimatter mixing within this framework.
So matter-antimatter mixing is this rare process where particles and their antiparticles can transform into each other.
And it's a phenomenon that's really puzzled physicists for decades.
It has, yeah, because if matter and antimatter were created in equal amounts in the Big Bang, they should have annihilated each other, leaving nothing but energy.
But obviously we exist, so there must be some asymmetry there.
Right, and the source explores how this matter-antimatter mixing could potentially be described within this multidimensional framework, offering new ways to understand the fundamental nature of matter and antimatter.
Wow.
And maybe even shedding light on this matter-antimatter asymmetry problem.
That's amazing. It's incredible how these abstract mathematical ideas can have such profound implications for our understanding of the universe.
It really is. It's a testament to the power of human curiosity and our drive to understand the world around us.
Absolutely. We've journeyed from the familiar world of knots to the mind-bending realms of quantum groups, braided geometry, and now polydimensional covariance.
What a trip.
It's been an incredible deep dive.
It has, yeah. It's been a real pleasure exploring these ideas with you.
Likewise, and if our listeners are as intrigued by these ideas as I am, I encourage them to explore further.
Yeah, go out there and dive into the world of mathematical physics.
See where your curiosity leads you.
You might just stumble upon the next big breakthrough in our understanding of the cosmos.
That's a great note to end on.
All right.
Until next time, keep those minds diving deep.
Take care.